In this presentation, we continue to talk about momentum, and specifically we look at the situation where momentum is a conserved quantity. So the law of conservation of momentum basically states that in the absence of any external forces, the momentum of a system remains unchanged. So when a quantity is conserved in nature, it basically means that that quantity is unchanged. And so what we're saying is that if we have a system of objects that are interacting with one another, but they're not interacting externally with anything else in the environment, then the total momentum of that system is going to remain unchanged. So here's an example of one of those situations. So I have a cannon and a cannonball, and that's on a frictionless surface. So when the cannon is fired, the force of the cannon barrel is equal to the opposite force from the cannonball. So in other words, there's an explosion here, and there's a force on the cannonball, and in turn there's an opposite force on the cannon. And those forces are equal and opposite according to Newton's third law. And so they actually sort of cancel each other out if we think about the cannon and the cannonball as our system. So there's no other forces other than those two interaction forces. So the net force is zero. So first of all, they're equal and opposite according to Newton's third law. And so what happens is that the cannonball gains momentum to the right, so it has positive momentum, and the cannon itself gains an equal amount of momentum in the opposite direction, which is to the left, or it recoils. So the total momentum before the interaction was zero. They were sitting at rest. There was an interaction between the two, and there was a force exerted, equal and opposite forces, and as a result, there was momentum from the ball in one direction and momentum of the cannon in the other direction, but the total momentum of the system before the interaction, which was zero in this case, is going to actually equal the total momentum of the system after the collision. So how can the momentum be zero after this interaction? Well, remember, momentum is a vector quantity, so the ball has positive momentum to the right, and the cannon has negative momentum to the left. Now the cannon has a much larger mass, so the recoil of the cannon is going to be a small velocity versus the cannonball, which is going to be a very fast velocity. So smaller mass of the ball, larger velocity, larger mass of the cannon, smaller velocity. But those two momentums are in opposite direction, and so they can actually cancel each other out to give us a total net momentum of the system to be zero. So a good way to think about momentum conservation is to think about collisions. So if you have a collision between two objects, then the first thing that should come to mind is momentum, and is momentum conserved? Because oftentimes in physics, when we're talking about interactions of objects, especially during collisions that occur for a short period of time, we say that momentum is conserved. So here we have two billiard balls, and they are headed towards one another. And then what can we say about the collision? So let's assume that these two billiard balls are on a frictionless surface, even though a pool table is not frictionless. We're going to assume we live in a perfect world and there's no friction. So they're heading towards one another at some velocity. They interact with one another for a short period of time. So if you've ever shot pool, you know the balls are not in contact for a long period of time. And so when they strike one another, ball B exerts a force on ball A, and that force is going to be to the left. But in turn, according to Newton's third law, ball A exerts a force back on ball B. So these two forces are acting on different objects, but they are a pair of forces according to Newton's third law, because Newton's third law's pairs of forces always are exerted on different objects. And so the net force on this whole system is just going to be zero, because these two forces are going to cancel each other out if we think about ball A and ball B as being our system in this particular case. So the balls had some momentum initially, and they will have some momentum afterwards, but we're going to see that we can have conservation of momentum. So in the absence of any external forces, these two forces are sort of internal forces to our system. They would cancel each other out. Then the momentum of a system is going to remain unchanged. So any forces that are interaction forces between the objects that make up our system are considered internal forces, and anything like friction or something applied to the two balls would be considered an external force. And here we don't have any sort of forces other than the interaction force between the two objects. All right, so let's go back to our picture. So we have the interaction. So the two objects exert forces on one another for some small time interval, but the forces are exerted over the same time interval. So these two objects don't have to have the same mass. They do have the same force according to Newton's third law, and they do have the same time interval where that interaction occurs. So I could look at the equivalent of Newton's second law for momentum, and I know that the force exerted on ball A has to equal the change in momentum of ball A over the time interval that that force was applied. The only force that's exerted on ball A is the force that ball B exerted on A, and that's going to equal the change in momentum of A over the time. I can do the same thing for ball B, and I know that the net force on ball B is the change in momentum of ball B over the time interval. The only force exerted on ball B is this force that ball A exerts on ball B, and that's going to be equal to the change in momentum over the time. So what we know is that the net force on the system is 0 because the force that ball A exerts on, the force that ball B exerts on A plus the force that ball A exerts on B, sorry, I switched those, has to equal 0. These forces are equal to one another and oppositely directed. So if I take into account the fact that this force of B on A would be negative, the force of A on B would be positive, these two forces are going to cancel each other out. But I can write down that the force that ball B exerts on A is equal to the change in momentum of A over the time, that's this piece, and the force that ball A exerts on B is the change in momentum of B over the time. And if I add those together, it has to equal 0. You'll notice I canceled the time out here, and that's because I could multiply both sides of this equation by time, and it would cancel out the times here, and if I multiply anything by 0, time times 0 is still going to give me a 0. So now what I can do is I can plug in the fact that the change in momentum of ball A is just the mass of A times its final velocity minus the mass of A times its initial velocity, plus the change in momentum of B is the mass of B times its final velocity minus the mass of B times its initial velocity. So here is the change in momentum of A, and here is the change in momentum of B, and that has to equal 0. In other words, the total momentum of the system is unchanged, right? So here's ball A, here's ball B, those are the final momentums, here are the initial momentums of the system, and if I add the change in momentum of A and the change in momentum of B, it gives me 0. So the total system does not change its momentum. So for an isolated system where the interaction is only between the objects that are colliding with one another during the collision, and there's no external forces, what we can say is that the net momentum that the objects have before the collision or the interaction is equal to the net momentum that they have after the collision. So if I take the previous equation and I rearrange it, and I take all the terms that were negative and I move them to the other side of the equation and keep the terms that were positive on the same side of the equation, I get that the momentum of A initially plus the momentum of B initially, that's the total initial momentum of the system before the interaction, it has to equal the momentum of A final plus the momentum of B final, or the momentum of the system after the interaction or the collision. So this is why we can say that momentum is conserved. So total momentum before is going to equal the total momentum after. And the way that we look at the total momentum of a system is we look at the momentum of each object separately initially, and then we compare it to what its momentum is afterwards. So in terms of physics, if you think about objects that are colliding with one another, the first thing that should come to mind is momentum. Is momentum conserved? Are these two objects interacting with one another and only interacting with one another? And if they are, then they're exerting equal and opposite forces on one another according to Newton's third law. Those forces are going to cancel each other out, and so that means that whatever momentum those objects had before they collided, it has to equal the same momentum that they would have afterwards. That doesn't mean their individual momentums will be the same. It just means that the momentum of the total system is going to be unchanged. So it turns out that there are two different types of collision. There's something called elastic collisions. In elastic collisions, momentum and kinetic energy are conserved. We haven't talked necessarily about kinetic energy yet, but we will talk about that soon. So this occurs in colliding objects that rebound without any sort of lasting deformation or generating any heat. So if you have two billiard balls or two pool balls that strike one another, that's pretty close to elastic collision. The balls are very hard, they don't deform afterwards. So anything that's very solid is going to be more elastic than something that is like a tennis ball. If you have two tennis balls that collide with one another, that would not be elastic, because when the balls collide, they actually have springiness to them, and they would change shape during the collision. So we could go to the PhET website that has a lot of simulations, and we could look at collisions. And so we're going to do that on the following slides. We're going to look at elastic collisions, and we're going to look at some different situations. When the objects are both moving, when they're not moving, when one object isn't moving, and so on. When they have same masses, different masses. So this is an elastic collision where I have identical masses. This says identical masses and different masses. So in this particular case, the objects both have the same mass. So I come over to my simulation picture and I notice that they both have the same mass. And object 1 has some initial velocity. Now I haven't hit play yet. I will hit play here in a second. But both of these have, both of them have the same mass. The red ball is going to have some initial velocity of 1. Since the mass is 1 and the velocity is 1, it has some momentum of 1 kilogram meter per second. The second ball is at rest. So the total initial momentum of this system is just 1. And the balls are identical. It's elastic collision. I'm going to hit play. I'm going to go ahead and pause it. So here, after the collision, the red ball came to rest, and its momentum is 0. Velocity is 0, and the second ball has a momentum of 1, velocity of 1. So in this particular case, ball 1 gives all of its momentum to object 2 because of the fact that this is elastic collision and they have exactly identical masses. So there's lots of different possibilities, and you don't have to memorize these. These are just some examples to show us what's going on. Oops, sorry, that's just going to repeat itself. So I have to go to the next slide. Okay, so here I have object 1, and you can tell that it's larger, so it has a mass of 2 kilograms. Object 2 has a mass of 1 kilogram, so the first one is bigger. It's traveling with the same initial speed of 1, so it has initial momentum of 2. And let's see what happens after the collision here. In this case, is ball 1 going to just stop, or is it going to keep going? All right, so ball 1 is still moving to the right, but it's traveling slower. It was traveling at 1, it's traveling a little bit slower now. And ball 2 was at rest, and now it's traveling fast. It's actually traveling faster than ball 1 was traveling initially, because it was only traveling 1. So now it has some momentum afterwards. So before the collision, only the red ball had momentum. Momentum is conserved. After the collision, they both have momentum. If I add up their momentums, 0.67 and 1.33, momentum is still 2 kilograms meters per second in total, right? Because momentum is conserved. This one also has a representation over here that we could watch, and we could see this is the momentum of 1 and 2, and here's the total, and you can see that the total does not change. So I'm going to go ahead and I'm going to backtrack it. Let's do it again. We can watch this. Here's 1. It has all the momentum, and then afterwards, right, oops, we'll pause it. Afterwards, it has less momentum. 2 has more, but the total momentum remained unchanged. All right, here object 2 has more mass, so its mass is 2 kilograms. Object 1 has 1 kilogram mass, still traveling at 1 meter per second. Let's see what happens here. Here is the total momentum before. Here's the momentum of ball 1 before the collision. So when ball 2 is larger, has a larger mass for elastic collisions and it's initially at rest, it's going to cause the one that was in motion to move backwards. So if I look at the total momentum, it's still the same. It started off with momentum of 1. It still has momentum of 1. The momentum of the green ball is 1.33. The momentum of the red ball is a negative 0.33. If I add those two quantities together, it's just going to give me back 1. So again, momentum was conserved. We started off with 1 unit of momentum, and we still have 1 unit of momentum afterwards. We have to take into account direction, and that negative direction added to the positive value will give us the same value we had before. All right, here we have 2 objects that are have the same mass. So over here they have the same mass, and they both have the same initial speed. Ball 1 is traveling to the right at 1 meter per second. Ball 2 is traveling to the left at 1 meter per second. So they both have momentum. If I look at their momentum values, they're exactly equal and opposite. So this one is 1 and this one is 1. Let's see what happens afterwards. So this is also an elastic collision. Oops. Okay, so after the collision, the balls are traveling in exactly opposite direction with the same speed they had before, just oppositely directed. So the green ball had negative momentum, and now the red ball has negative momentum, and vice versa. So momentum is still conserved. We started off with 0 momentum to start with, and we have 0 momentum afterwards. Even though they're moving, they have 0 momentum because of their direction. We can also have something called an inelastic collision, and during inelastic collisions, only momentum is conserved, kinetic energy is not. In nature, most collisions are inelastic. Most of the time, there's some sort of deformation, there's some heat loss, and so it's very rare that we actually have perfect elastic collisions. So we're going to focus on that simulation again, but we're going to look at perfectly inelastic collisions, and those are situations where objects actually stick together afterwards, and let's see what happens under some different circumstances. So here I have identical objects, just like before. The red object has a velocity of 1, so the initial momentum of the system here, total momentum is just 1. And let's see what happens afterwards, traveling at 1 meter per second. They're going to stick together. So now they have to share their momentum. So after the collision, it's hard to see this because it's covered up, but each of them, we can see it right here, each of these after the collision has a momentum of 0.5. So the red ball started off with 1, and then afterwards, because they have the same mass, it shares its momentum between the 2 objects, which means it's split in half, and the velocity is half of what it was before. Now that's because they have the same mass. If object 2 has a larger mass, so now because of the larger mass, it has more momentum to start with, and it's going to strike an object that has a smaller mass, you can kind of make a prediction about what's going to happen when they stick together afterwards. So when they had exactly the same mass, that velocity that they had split evenly between them. So now let's see what happens when this has more mass. So now, instead of that velocity of 1 splitting evenly between them, it actually is going to be such that the velocity is larger. So this ball has a lot of momentum, and so when it strikes the other ball, momentum is still conserved, but the balls are going to be traveling faster than half of the original speed. Same exact example, except now the red ball has a smaller mass compared to the larger mass, same velocity, same initial momentum of 1, and let's see what happens. Now they should actually be traveling slower afterwards, right? So now instead of going half of that speed, they're less than half that speed because this ball has a lot of mass, a lot of inertia, and so that speed is going to be less. So those were situations where the object sticks together after the collision.